Hello everyone, my name is Daksh and I'm glad to present our work on data-driven stochastic modeling using autoregressive sequence models. This is a joint work with Shunri and my advisors Jing and Hong. To motivate this talk, let me start with a service system, say a hospital. Nowadays, there are information systems in place for these service systems that collect operational information, which usually takes the form of events table. Now, suppose we want to analyze this system. For example, we might be interested in identifying bottlenecks or do some kind of policy optimization. The question is how to do that. And the usual answer is let's do stochastic modeling. Now let's see how conventional stochastic modeling works. So imagine this hospital has an underlying queuing network where patients arrive, they check in, and they proceed to different services. Note that this queuing network is not known to us in the first place, and our main job as stochastic modeler is to build a queuing model for this service system. However, this requires a lot of queuing expertise to build a correct model. And this is the key drawback of the conventional stochastic modeling, as it limits its widespread adoption. To remedy this problem, we introduce autoregressive sequence models for stochastic modeling. Our approach relies on predictive framework of stochastic modeling, which I will explain in a moment. And to enable this predictive framework, we leverage two broad things. First is rapid progress made in machine learning and AI for modeling sequential data. As we will see later, our approach requires only basic coding skills and minimal queuing expertise. And this really democratizes the benefits of stochastic modeling. Second, it leverages large amount of operational data. As a result, our approach being data-driven has potential to model non-conventional systems. For example, service systems operating under non-stationarity. Predictive framework relies on the jump process representation of queuing dynamics, where we represent it as a sequence of events and inter-event times. Using this, we can express the queuing dynamics as an autoregressive product of conditional probabilities, which is equivalent to the probability over the sequence of events and inter-event times. Using this, we have the predictive framework where we frame a single learning problem, predict the next event and its time given the history. Basically learn the conditional distributions we saw earlier. And to learn these conditional distributions, we fit a high capacity sequence model via stochastic gradient descent. And once it is trained, we can then simulate trajectories from this sequence model using autoregressive sampling. This is in contrast to the conventional stochastic modeling, where we first select a queuing model, calibrate its parameter, and then build a discrete event simulator. Now, natural next question is there any sequence model which can learn these conditional probabilities? Fortunately, deep learning has made substantial progress in sequence modeling. For example, LLMs now achieve SOTA performance on a wide variety of text-based tasks. The underlying architecture which empower most of these models is the transformer. Further, dealing with transformer architecture also has become a lot easier, as they have become much easy to code and also economically accessible. In this slide, we also use transformer as our underlying architecture. However, our framework is agnostic to this underlying architecture and can be adopted to potentially better architectures in future. Therefore, our framework can be divided into two stages. First, train the sequence model using past operational data, and then in stage two, use it to simulate trajectories of the service system autoregressively. To demonstrate the effectiveness of our framework, we do rigorous empirical evaluation of our approach by testing it on diverse systems, including Markovian and non-Markovian queues, system operating under non-stationarity, and queuing networks with tandem servers and abandonment. Our experiments show that this framework is flexible and effective in modeling all such systems. In addition to this, our framework also possesses two other key abilities. First, it has the ability to quantify uncertainty in performance measures when the parameters of the service system are uncertain. Second, it has the ability to evaluate counterfactuals. We demonstrate it on a staffing decision problem where the policymaker needs to decide how much servers to employ each day while facing different arrival rates across days. In the end, let me give the key theoretical insight of why our approach works. Our key result is that the Wasserstein distance between the predicted distribution and the true distribution for some performance measure is upper bounded by this term on the right, where the first term is error suffered due to imperfect training, and second term is error suffered due to limited prediction length, which even a perfect model will suffer. And the key takeaway message is that our model is as good as we can train it. With this, I conclude. Thank you for your attention, and please refer to our paper on this link for more details.